Lesson 22, Curve Sketching 7, Even Functions. Now this is a very useful technique for sketching. If you know a function is even, that will halve the workload. Let me demonstrate this with the first one. It's a known function, function x equals x squared plus 1, which I've sketched on the right hand side here. Now, to test if that's an even function, we'll put in a value for x. So I'll put in function 1, and I get 1 squared, which is 1, plus 1, which gives me 2. So here, this is the point 1, 2. Then we put in another value, function minus 1. That is exactly the same value, but it's the left-hand side of the function. And we get minus 1 squared is 1, plus 1 also equals 2. So function 1 equals function minus 1. Therefore, this is an even function. We can't say it's definitely an even function because we've only selected one value, but it would be enough for us to be able to sketch this. So if the y values are the same, well, you put in the corresponding values for x, when it's changing the sign, then it's an even function. Now, a more formal way of doing this, and this is what you'd be asked to do if you're testing this in the exam, we'll say for a value x equals a, we see that function a is a squared plus 1. Function minus a, and you need to do this, is minus a all squared plus 1, which is a squared plus 1. Therefore, function a equals function minus a. So therefore, function x is an even function, because this is true for all values of the function. Now I'll go on and do a couple more now. Alright, now here is example 2. Now I'm just going to check formally if this is an even function. So I'm going to let x equals a. So function a equals a to the fourth, which is a to the fourth, plus a squared. And function minus a equals minus a to the fourth, plus minus a squared. Now if we raise this to an even power, this will be changed to a positive, so it becomes a to the fourth, same with minus a, and we'll get a squared. Therefore, function a equals function minus a. And this is the case when these are even powers. So notice this is an even function, right? So it'll be doing something, the same thing either side. Okay. Alright, so let's just check out a few points now. First of all, the obvious point is x equals 0, so we can see it function 0 is going to be 0. So we'll have a point here. And we'll try the old function 1, that's quite easy. And putting that in, we get 2. And there's a 2 there. And obviously for 1, that'll be 1, 2. And on the other side, we're going to get the same thing here. So straight away, it makes life easy. So what's this going to look like? Now, this is a quartic curve. Now, it's just useful to know the various shapes of the quartic. The quartic can just be like the parabola, or it can do this funny sort of thing like this, with a point inflection here and a minimum, and this one. It can also go upside down, but we know this one's not going to go upside down because we've got a positive sign here, and also for the very fact that we're getting this situation. So we could have something like this, but that would be, this one's sort of ruled out, isn't it? Right? Because that's not even. Right? So it could be this one or this one. All right. So let's have a look at I'll bring in the calculus now, and we'll differentiate this, and we get f dash x is equal to 4x cubed plus 2x, And we take out the 2x, and we're going to get here 2x squared plus 1. Now if we let it equal 0, we'll see that x will be equal to 0, and that's it, because this can't be equal to 0, so it must have been the shape here. Alright, so we can just draw that down here like this. Sorry, not very good. A bit wobbly. Very wobbly. Okay. It's hard to do with it on a tablet. Okay, and that's the shape. You can go on and look at the second derivative if you wanted to. Not really necessary, but we'll do it anyhow. And we get 12x squared plus 2. Now you can see straight away that that can never be equal to 0, so we can never have any points of inflection. So that it would rule out this one here. Again, rule that one out, definitely. So this is the only curve it could possibly be. And that's how an even function can help you. All right, I'll go on to another example. And it'll go a little bit more difficult. Okay, now this one here is quite an advanced type. But you can see it's not too difficult if we know it's an even function. Again, we'll test this out. So we'll let, again, x equal a. So function a equals 1 over a squared plus 1. And function minus a equals 1 over, again, a squared plus 1. Now you don't have to do this if you're sketching it. This is just unless you're asked to do it. But so you can actually just observe really that's going to be an even function. So function a equals function minus a, therefore it's even. Right, that's quite nice to know. Now we'll put in our standard function 0, and this time we get 1 over 1, which is 1. So we have a point here which is at the point 0, 1. Now again I'll put in function 1 again, the easy points, and that gives me a half. So at 1 it's a half, and of course at minus 1 it also must be a half. So we can see there that the curve is going to go down. Now the next thing is, if we look at our function, our y values, it doesn't matter what we put in here, right? This is never going to be negative. And because it's even, it's going to be negative on this side. So we can actually, we realize then that this curve will go down here and approach that line. We can test the point. If we put in, say, 10, we're going to see 1 over 101, which is very, very tiny. And same thing goes on this side. And we could play our limit theory too as well, but after all, we're just sketching this. You'll notice some points of inflection here. Now, if we're asked to find points of inflection, then we'd have to differentiate this. So we'd say f x equals x squared plus 1 to negative 1. And we find f w dash x equals, now this will be minus bracket x squared plus 1 to the minus 2 times 2x, which is going to be equal to minus 2x over x squared plus 1 all squared. All right, now I've cheated a little bit, and I've gone ahead and worked out the second derivative using the quotient rule. And now we'll see that 3x squared minus 1 equals 0, which gives that x equals plus or minus 1 on root 3. So these will be the values for the points of inflection. Now 1 on root 3, that's root 3 on 3. That's about, yeah, it's in here a bit. Point of inflection starts actually in here. And then you just simply substitute this value in here to get the y value. And putting, let's just do that. Function 1 on root 3 is going to be 1 over a third plus 1, which is 1 over 4/3, which is 3/4. So that would be point 1 on root 3, 3/4. But it's nice, isn't it? Because on the other side, you just write down minus 1 on root 3, 3/4. All right. Now, you'd only work those points of inflections out if you're asked to do that, right? So otherwise you just would draw the curve as such. And that completes that little section on even function. The next section will be on odd functions, and that also helps enormously when you're sketching functions.